All right, good afternoon, everyone. So we have three more lectures remaining, and we'll be covering the induction motor in that three remaining lectures. If you have understood permanent magnet synchronous motor, the operation of it, then induction motor is extremely simple. All you're going to be doing is taking the rotor, replacing it with a rotor that does not have a magnet. And somehow surprisingly, it induces a magnetic field on the rotor, and it behaves very similar to what a permanent magnet synchronous motor behaves like. Right, so we'll do a quick review again of this permanent magnet synchronous motor. We won't get into the equations today. We're just going to get a feel for it using just space vector notations. And we'll extend the same concept when we go to induction motor. Right, so we have spent 5 lectures now on permanent magnet synchronous motor and the stator winding. So this will be a quite quick review of it, and then we'll jump to induction motor. So what we saw so far, that we have a stator, we have sinusoidally distributed windings, which are phase shifted by 120 degrees. So when I draw this diagram, the B field of the A phase is maximum along this direction. B field of the B phase is along this direction maxima. So B field of C phase is along this direction with its maxima. And then it's sinusoidally distributed everywhere else, right? So the positive maxima is here, negative maxima is there. And as far as the conductor density is concerned, if I draw this loop around this direction, the maximum conductor density, conductors for A phase is 90 degrees away from it, right? An easy way of visualizing this is if I form a loop like this, the B field of that loop will be along this direction. So if the B field is maxima here, the conductor density would have to be maxima perpendicular from it, right? So this is what we have. The structure remains exactly the same whether we go to a permanent magnet motor or an induction motor. We are going to retain the stator structure. The only thing that will change is what we are going to put on the rotor in the induction motor. So once we have this, we have our expression for our conductor density distribution, Na of theta, which was N divided by 2 times sine of theta. Let's look at just 2-pole case to keep it simple. And once we have this, you know how to figure out the H field in the air gap. You know how to figure out the B field in the air gap for every single point, for every single winding. And then you know how to figure out the net B field in the air gap, basically summing up all of those three, assuming superposition holds without any saturation. Then you can figure out the net B field. And we've introduced the space vector notation, BMS, to capture where the net B field is at its maximum. Right? So whenever I draw the space vector notation, it is basically capturing where the maximum B field is. At time t equal to 0, if I'm passing currents that are in this form, if I'm passing a current Im cos omega t in the A phase, Im cos omega t minus 2 pi by 3 in the B phase, and Im cos omega t minus 4 pi by 3 in the C phase. Then at time t equal to 0, the current in the A phase would have been at its maxima. The B field in the A phase also would have been at its maxima because of that. And the space vector is going to be aligned along the A phase. As time goes on, as the A phase current starts to reduce and the B phase current starts to pick up the slack, the B field is going to start to rotate, right? So you can think of the maximum of the B field rotating around, and then everywhere else it will be sinusoidally, spatially distributed in a sinusoidal manner. So going forward, you can forget about all the other distribution that we have. You can just visualize the B field alone, the peak of the B field alone as a space vector that's rotating in time, right? So it has nothing to do with the rotor. We just have 3-phase stator windings. You pass sinusoidal currents at any frequency, and the space vector is going to start to rotate at the frequency, right? So we are just capturing the peak alone using this notation. So if my BMS space, So if my BMS space vector is along this direction, right? By BMS, I mean the magnetic field in the air gap. Due to stator currents. Yes. What is going to be the direction of my stator current space vector? Yep, sorry, Trisha.
I just have a question. What's the difference between NS and NSP again?
Could you repeat? I can't hear you. What is the difference between NS and
NSP.
NSP?
Yeah.
Oh, NS is total number of conductors per phase. NSP is NS divided by P, which is the total number of conductors per phase per pole. Right, so if you have 100 conductors in your motor and you have two-pole motor, your NS is basically 100 and your NSP, the number of conductors per pole is 50. If you have a four-pole motor, the number of conductors per pole would be 25. Right, this is a useful notation because the common idea is when you wind motors, you would try to keep, when you go to a higher pole count, you would try to keep this NSP number the same. Right, because the maximum H field at any point in the air gap is determined by NSP. Because when we had our case where a two-pole motor and we had some 50 conductors in total here, then the B field here would have been decided by what was the total number of conductors within this section, right? Which was 50, you would have had some mu naught times N divided by LG times the current. So this number of conductors determines what the peak B field is going to be. If I'm doing a four-pole motor, and if I were to reduce the number of conductors, let's say I have the same 100 conductors, NS. So in this case, here would have been 50, here would have been the other 50. When I go to four-pole motor, there would just be 25 conductors here, 25 conductors here, 25 here, 25 here. Right? So the total B field compared to here, let's say this was 1.1 Tesla, here it's just going to be 0.55 Tesla because the number of conductors half for this big loop that I'm choosing. Right? But when, as a motor designer, what you would rather do is you'll always utilize the core to its maximum possibility. So you would want to push the current or the number of conductors as much as possible so that the peak B field along the teeth or along the yoke is at its maximum value which the iron can support, let's say about 1.1 Tesla. So it makes sense to have NSP constant. So you would have to put 50 here, 50 here, 50 here, and 50 here. Right? So for a four-pole motor, you can basically increase the number of conductors while keeping the same maximum B field. Right? So that's the reason we introduced this new terminology NSP. As a machine designer, as people who are trying to understand how a motor works, NS is a useful term, but as a machine designer, they would usually talk about NSP. If that is constant, then the torque can be increased if you increase the pole. Okay. Any other questions? So if my BMS space vector is, let's say, along x-axis, or let me pick some other random axis where always. So at some time t, omega t is at 30 degree. Let's say BMS space vector. So this is the A phase magnetic axis. Let's say some angle 30 degree. Where will my stator current space vector be? What will be the direction of my stator current space vector for that arrangement that I've shown there?
Same as BMS, right?
Same as BMS. Right, because again, going back here, if I were to look at what the stator current space vector will be at time t equal to 0, A phase current would have been at its maximum. And what is the idea of space vector? Again, it's tracking where the maxima is. That's all it's doing. There are other ways of looking at the same thing as well. So if you had, so our BA would have been some mu naught NSP times I divided by LG times IA times some cos of theta as a function of theta. If you're so, and then we have BB of theta is mu naught NSP LG times IB. So instead of worrying about the spatial distribution of the B field, let me look at only where the B field for the A phase is maxima. It will be along this direction. Where will the B field for B phase be maxima? It will be along J2 pi by 3. And the B field for C phase, it's going to be at its maxima at mu naught NSP divided by LG times IC e power J 4 pi by 3. Now what I'm asking is the space vector BMS is basically indicating where the sum of these three would be at its maxima. This is already at its maxima. This is already pointing to the direction of its maxima. This is already pointing to the direction of this maxima. If I sum up these three, that would basically give me what BMS space vector is. And what is on my right hand side? IA e power J0, IB e power J2 pi by 3 plus IC e power J4 pi by 3, which is exactly what the definition of the current space vector was. Right? So wherever your BMS is pointing to maxima, that is where your stator current space vector is going to point to as well. So this is quite useful because going forward, you don't need to think about every time when I ask you where the current space vector is going to be at its maximum, you don't have to visualize what the current values are going to be and try to figure out where the current space vector is going to be. If I tell you where the BMS space vector is, the relationship between BMS and the current is just a straight constant function. Right? It's just a constant scaling that you have here. So B is just related directly to the I. So if the current space vector moves somewhere, the BMS space vector is going to move along with it. Or if the BMS moves, current will move along with it. Right? So, okay, so this is where my those two space vectors that we draw here. So, okay, where is the rotor space vector going to be? Rotor magnetic field space vector. Yep, Lily.
Well, we have to know the load angle, and then it will be the load angle from BMS.
Perfect. Will it be behind or up, forward?
It'd be lagging behind.
If it's lagging, what is the condition?
It doesn't. It's either generating or motor.
Okay. So if it's lagging, is it a generator or a motor?
Motor.
Motor. So exactly what Lily said. So we can have the BR anywhere, but lagging by some angle delta. If the space vectors are rotating along this direction, then this is lagging behind, in which case the diagram that I've drawn is in motoring mode. Okay. But again, it's very critical that you remember at steady state, all of these space vectors are rotating at the same speed. Right? So you can have an angle difference between these two. It can lag behind, but they are rotating at the same speed. So think of like you are going in a car and you're towing something in the bed behind your car, connected to some spring. Right? Both of the cars at steady state must be at the same speed. You have some spring connected and you're towing this, at steady state, these two would be at the same speed. Now, instead of towing a car, let's say you're towing some big truck. The spring is going to be stretched. Your load angle is going to be larger, right? But both the truck and the car would have to go at the same speed at steady state. That would be the requirement for steady state, right? So whenever you apply more load, think of swapping the car that you're towing to some other heavy load that you're towing. The spring that's connecting these two cars are going to stretch out. And that's basically the delta angle increasing between the two. And it can oscillate back and forth, back and forth. Let's say some sudden boulder falls on this rock and you're still having the power to pull it through. It'll go back and forth, back and forth. There'll be some oscillations going on. But at steady state, they would have to stay together, right? So this can go back and forth, swing around, go and settle in a new angle, but they're all rotating at the same speed at steady state whenever we draw a steady state diagram. In the textbook, we only consider steady state. In the class, we have considered transient case as well. But whenever you see the textbook diagram, it's completely steady state. So all of these space vectors are rotating at the same speed. Okay, now that BR is here, where will the EMF space vector be? EMF due to the rotating magnet. There are two EMFs. One EMF we have already accounted for, which is basically the current that passed through the inductance LM coil, right? LM or magnetizing inductance. That created this BMS magnetic field. And the voltage across this LM would have been the EMF due to this magnetic field that was set up in the air gap due to the stator currents. Now we are going to look at the EMF due to the rotor magnetic field varying. Right? What will be the direction of the EMF of the rotor magnetic field? The space vector for the
90 degrees ahead
90 degrees ahead of
of the rotor magnetic field.
rotor magnetic field. So our ES space vector is going to be 90 degrees ahead. Why is it 90 degrees ahead? What relationship did you use to figure that out? Okay, we can calculate the EMF for each of those spaces, which was the homework problem. Take that EMF, plug it into the space vector transformation, and it will tell you that it's clearly 90 degrees ahead. But there's a much easier way. So all the equations that we have derived, when we go from three-phase entity to space vector entity, if we have balanced voltages, or we have three-wire system, in case currents may or may not be balanced, but still the sum of the currents will be zero, then the space vector transformation doesn't lose any information going from ABC to space vector. Right? So whatever equations we derive on the time domain will all hold true for every single phase, will all hold true even for the space vector notation. As long as the transformation is linear. I'll show an example where it will fail when the transformation becomes non-linear. But the idea is if you double your current in each of these phases, your space vector magnitude is going to become double. If you add 5 amperes to this and some ampere to this, some ampere to this in such a way that it's still balanced, then that will be effectively adding another space vector to this space vector. Right? So if it abides by the principle of scaling and it abides by the principle of addition, when you go from one transformation to the another, then the linearity is conserved in the system. So as long as you do any linear modifications here, that will hold true with the space vector as well. So what linear operator can you use to explain the angle difference between BR and the ES space vector? What is the relationship between back EMF and the EMF? Sorry, the magnetic field and the EMF?
Derivative.
Derivative. So RE is going to be equal to sum n times d phi by dt, or basically d lambda by dt. And this phi itself is going to be a function of your magnetic field dr. Right? It's some magnetic field coming from the rotor interacting with the coil area. All of those are constant. The only variability is this BR term. As the rotor rotates, this BR is going to be changing in the air gap. And that is what is creating this d phi by dt. And I said, what was my statement? That all transformation, as long as they are linear operators, you did in the phase domain, all of those hold in the space vector domain as well. And the linear operator here is differential. Differential integral, all of those are linear operator. So if I know where my BR space vector is, then I can quite easily find out what the ER space vector is going to be. So let's say this BR space vector is BR space vector is some BR magnitude times e power j omega t. Now your EMF space vector, since this expression holds in the phase domain that we derived, it also holds in our time domain. So it's going to be some area equivalent times your BR divided by dt. That's our flux. Right? So n times area, you can bring out area equivalent, whatever that is, times d by dt of BR peak e power j omega t. If you do this differential, you end up with NA peak BR j omega t differential. You will get a j omega outside times BR peak e power j omega t. This term comes from differentiating j omega t term, right? And this again, that's why your EMF is dependent on the speed. But then the part that's of interest to us is this j term. That is basically same as saying it's e power j pi by 2. Right? That's just cos of pi by 2 plus j sine of pi by 2. This term is 0. This term is j. Exactly what we have there. So what is this e power j pi by 2 doing? That's basically the rotational transform. You take any vector, multiply by e power j theta, it's rotating the vector by an angle of theta. So that's exactly what we have done there. So wherever our rotor magnetic field is going to be, in turn the rotor flux direction is going to be pointed that way, flux linkage is going to be pointed that way. You take the differentiation of it, you get a j term added onto it, which is basically rotating this vector by an angle of 90 degrees. Right? Where is my terminal voltage space vector going to be? How do I figure out where my terminal voltage space vector is?
The sum of the current space vector and the EMF space vector.
Is it the sum of the current space vector and the EMF space vector? Those two are two different entities. You're basically saying adding up something with units ampere and something with units voltage. You're on the right direction. Is it just the current that I add to the E space vector?
And the resistance of the stator.
Perfect. So we have our current space vector along this direction. We need to figure out what the drop in the resistance is. So this is Lm plus LL, leakage inductance. And then we have our back EMF here, E space vector. And then we have our terminal voltage V here. So take your EMF space vector, add whatever voltage you dropped across the resistor, add whatever voltage you dropped across the inductor, whatever remains would be your voltage. Alright, so again, since these are all linear operation, whatever you did in time to is individual phase equations, you can use the same set of equations to do the space vector calculation as well. Or alternatively, you can do the same thing again. Look at the thing for all three phases. Right, this is the EMF of B phase, this is the voltage of B phase, voltage of A phase, current of B phase, and similarly another circuit for the C phase. Right? Figure out all of the three voltages individually by solving the circuit. And then you plug this voltage into the space vector transformation. It will be the same as if you just considered the space vector itself as a circuit variable. Right? Instead of doing this, if I consider this as a circuit variable, this current itself as a circuit variable, and the EMF space vector itself as a circuit variable. It's a single circuit that can quickly solve around. Right? So we take this, add IS space vector times RS. So IS space vector is along this direction. IS RS would be along this direction. So it will be parallel to IS. So this will be IS space vector RS. And then we have a drop across the inductance, which will be along. If I were to account for the drop across the inductance, which direction would I draw my space vector for that?
$90 degrees lagging.
90 degrees lagging. Is it lagging?
I'm gonna guess leading.
Leading, because what is the relation between the current in an inductor and voltage in an inductor? Current lags the voltage. We are interested in finding the voltage drop across the inductor. Right? So the voltage of the inductor leads the current by 90 degrees. Right? So if our current direction is like this, our voltage is going to be omega, whatever our frequency, grid frequency is, times Lm plus Ls times our current space vector. So this is the total effective space vector of the voltage. So we have space vector. Right? So there is a relationship between space vectors and phasor diagrams that you have drawn for AC circuits. If you take the space vector and take a screenshot of it at any particular time, I'm drawing it as if it here in the drawing, since I can't draw something that's rotating continuously. It looks as if it's a fixed value, but in reality, when you visualize this, in your brain, it should all be continuously rotating. That's what space vectors do. All right. When you go to phasor, it's basically taking a screenshot of this space vector and drawing it for one particular time. That will give us the phasor value. In addition, you scale the value by a factor of 2 by 3. Because if your magnitude of your current is some 10 ampere, your space vector magnitude will be 3 by 2 times 10 ampere. But when you draw it as phasors, you will draw the magnitude of the current itself as a phasor value as just 10 ampere. Right? So when we draw our phasors, it would have just been Im. But when you draw space vectors, that would have been 3 by 2 times Im. Right? So if you want to take your space vector and convert it to phasor, take a screenshot at one particular time, which is exactly what I've drawn here. Scale all of these space vectors by a factor of 2 by 3 to take out this value, and then you have your phasor representation. Right? Do you have any questions? Yep.
Just like if you were to write down a space vector, like on the homework, it says like write the space vector. How do you like label the angle? Do you use the same notation as a phasor, or is it different?
Which angle? So you would use this e power j omega.
Okay.
Whatever.
So like the angle is like a function of time, basically.
Yeah.
Okay.
So it will be e power j omega t, z power j times brackets omega t minus whatever the angle equivalent is. So in this case, if you're drawing this, it will be e power j omega t minus pi by 3, pi by 6. Right? So, any other questions? Okay. So let's let me ask what would happen if I make my frequency negative? If I were to, in the currents that I have there, mathematically, I yet do not know what negative frequencies mean. That's a term we are just introducing. So Im cos negative omega t minus 4 pi by 3. What does that negative frequency mean? Let's say somehow mathematically for a motor, I'm able to generate negative frequencies and give it to the motor. What do you think? What do you expect the motor to do? Yep, Zach.
In a different direction or no?
Perfect. So previously for the positive frequency, if it rotated like this, for the negative frequency, it's going to rotate in the opposite direction. So let's just quickly modify this and see what's happening. Cos of negative angle is just cos of omega t. What would this term come out to be? I want to remove the negative term from the frequency. What will it come out to be?
Omega t plus
Omega t plus 2 pi by 3, which is exactly same as saying it's omega t minus 4 pi by 3. Right? So plus 2 pi by 3 is the same as negative 4 pi by 3. Okay? So plus 2 pi by 3 or negative 4 pi by 3 are both one and the same. And then we have omega t plus 4 pi by 3, same as saying it's negative 2 pi by 3. And here we have Im cos. If you pull that negative out, it will become omega t plus 2 pi by 3, which is same as saying it's negative 4 pi by 3. Right? And then we go back to the answer that Zach gave. What we have effectively done is we have swapped the phases of B and C phase. What was previously B, if you look at the diagram on the left, now became C. and what was previously C became now, if it became phase C. So when you swap the phases, we know that if you do single swap, then the speed would rotate in the opposite direction. If you do double swap, it goes back to the original rotational direction. That's all it means. So mathematically, when we see this expression of negative frequency, in reality, what that means is I've swapped the phases of the motor. That's how we represent the phase sequence by putting a negative frequency there, just pure mathematical sense. And this will come back when we go to induction motor, where we'll see the rotor would have sometimes negative frequencies. Don't be alarmed, it's just that the phase sequence on the rotor has reversed. That means the direction is reversing in some sense. So this is all our permanent magnet synchronous motor is. So let's quickly, we have looked at the PMAC, we have looked at the torque is missing. So the total torque, again we have derived this, so I'm not going to redo the derivation. Pi RL BR times IM times sine of delta. So this was the equation we got for the net torque in the motor. We can rearrange these terms a little bit and clean it up. Pi times RL times BR times 3 by 2 IM times sine of alpha. Now this expression that we have here looks nothing like what we had for our Lorentz force equation. So our Lorentz force equation was some nice beautiful equation L times I cross B. And then when we went to torque, that was just multiplying by the radius RL times I cross B. But here we have a bunch of terms. We have a pi, we have this 3 by 2, we have this sine of alpha. None of that appearing in the Lorentz force equation, right? But once you convert this to space vector notation, it will become quite powerful. So BR magnitude is same as saying some BR space vector and its magnitude. 3 by 2 IM is the magnitude of the current space vector, right? IMS, current space vector magnitude, because that's going to be 3 by 2 times the phase peak. And then we have sine of alpha. Is there another way I can rewrite this expression? Cross product. So this is same as I times R times L, IMS space vector, cross product, BR space vector. So we have the same expression, some RL, some I cross B, some I cross B space vector. Right? So it has more beauty to it than what, the reason I introduced the space vector notation is not just to cloak away the complexities of the magnetic field in the air gap and stuff. There's much more beauty to it that makes us appreciate it much better looking at it in space vector notation. Perfect similarities. Can somebody tell me where that pi comes from? I missed that. NS by 2, NS by 2, NS by 2. Where does that pi term come from? So again, whenever you see these terms coming around randomly, go back to Fourier. We spend quite a bit of time on Fourier exactly for this because it keeps repeating again and again and again in motors. So when we had, where did we get pi in when we did Fourier transform? When we took some sine of theta, multiplied by sine of theta and did the integral over half cycle, we ended up with pi as the value of it, the LHS of it. Where is that sign coming from? In our case, the representation that we have here, we are just looking as if BR is some constant value, right? But that is not the case. BR is varying sinusoidally in the air gap as some function sine of theta. Our current space vector, again, a conductor density is varying sinusoidally as sine of theta across the air gap. So you have product of sine of theta, and the average of it when you integrate it will give you the pi factor that's coming here. Right? So this information captures as if the current and the BR are constant at every single location, which is not the case. We have sinusoidally distributed both B field as well as the current density distribution. So that when you do the average of it, that will give you the pi factor that we have. Okay. Do you have any questions? So let's go to induction motor. So in case of an induction motor, the rotor, which was previously a permanent magnet, which was shaped in such a way to have a sinusoidal distribution, gets replaced by what's called a squirrel cage. So the rotor structure that we have, that gets replaced by this bar arrangement that we have here. So what this is basically, right? So we take a whole bunch of copper rods and we solder the ends of the copper rod on the top and the copper rod on the bottom, right? And we have this set of, we will put this all inside stacked iron plates. And then we have these set of copper rods which are going to be carrying the current and creating the magnetic field. And on both ends, they are completely shorted out. For our simplified assumption analysis, we are going to assume the resistance of these, so these end rings that you see there, that's called end rings. And we are going to assume those have zero resistance. The copper bar going through, those we are going to have assume they have some resistance, rotor or whatever. So we are going to assume some finite resistance for the rotor bars, which will be quite small and the currents will be extremely large. But we would assume that the end rings are close to zero resistance and we won't consider it in our analysis, but we can account for it towards the end, that mistake in our assumption, right? And we have this whole apparatus put inside the iron core. Why do we have to put that iron core? Why can't we just have the copper bars? What's the iron core doing there? So if I were to remove off this iron core right in the middle and just have a bunch of copper bars for the rotor, would I lose out on anything?
Reluctance,
Was it?
reluctance.
Reluctance, perfect. So when you don't have that iron core, the magnetic field that's coming from the stator is going through a very large air gap, right? And when our air gap length becomes large, our equation was mu naught NSP divided by Lg times I times cos of theta was the magnetic field due to the A phase winding. That Lg factor becomes extremely large. So you want to make that Lg as small as possible. And that's the reason we introduced the iron core in the rotor as well, so that when the magnet goes through the pathway, it has just this tiny air gap Lg. If there was no iron core, just copper bars, then the Lg distance becomes very large and your magnetic field will become extremely small. So we put that iron structure in between. And what is the reason that these are iron plates, not a solid block of iron?
Prevent eddy currents.
Eddy current losses. If you had solid block, there's going to be a huge amount of eddy current losses. When we cut them into tiny slices and laminate those slices, we prevent eddy currents from becoming too large. All right. So the rotor structure, similar to even when you went to a permanent magnet synchronous motor, the rotor structure would have been similar, except they wouldn't have been slots on the rotor. You would have just stuck the magnet, at least for surface permanent magnet, you have stuck the magnet to the rotor surface. In case of an induction motor, you would put slots into this rotor structure and put these copper bars and weld the copper bars on both sides. If it's a very high power motor, you will have copper bars. If it's a low power motor, typically consumer side applications, you would use aluminum bars because aluminum is much cheaper than copper. But when you get to very large currents, very high power, these could carry your input current coming from the grid might be just a couple of amps, 3, 4, 5 amps. But the rotor bars themselves could be carrying hundreds of amperes, right? Because these are shorted bars with very low resistance. So you apply even tiny amount of voltage, it's going to carry a huge amount of current. All right, so you want to keep the resistance as small as possible. We have a stator structure, we have rotor, and there are a bunch of bars. So I'm looking at it from the top view. So these bars go all the way behind the board. This is the rotor, and then stator, we still have the sinusoidally distributed winding. That still remains the case for the stator. That hasn't changed from a permanent magnet synchronous motor versus an induction motor. Right, so each of these bars are basically shorted on the top and shorted on the back as well, with some finite resistance for each of the bar within them. Okay, so what we are going to first try and do is figure out what the EMF across each of those bars are going to be. Right, each of these loops. So I'm going to consider one bar here, one bar going inside, and these are again shorted through the end rings, and then back again there is another end ring which is shorting it, so that forms a nice loop. How do I figure out what the EMF across this loop is? How do I go about deriving that?
d phi dt, d phi dt.
D phi dt. So EMF across the loop is d phi by dt. What is the number of turns? It's n d phi dt, right? What is the number of turns? 1. It's just one single loop, solid shorted copper bar. And in a minute, you'll start to see that the beauty of this, all of these bars are exactly the same. It is the exact same thickness, exact same length. Everything is absolutely same about them. But they will somehow create currents and voltages which are different in each bar. Right? So that's what we're going to head towards. Okay, so the flux is what? Basically the flux through this loop. Right? Do I know the flux through that loop? Can I calculate the flux through that loop? How? Ni? Which Ni?
Okay.
Of A phase?
Yeah.
But there's also B field due to B and field due to C. And last time, if you remember, I said that the picture of the B field in the rotor is extremely complicated. And it's almost impossible to figure out what the B field would be analytically. But what is the B field that we know of? Because remember, let's say the BMS space vector is pointed along this direction, right? So let's say this is the direction of the BMS space vector. So what the field lines would look like. So it's quite a bit complicated to figure out what the B field perpendicular to the exact loop that I've chosen to be. So how did we get around it?
Flux on the surface.
Perfect. Which surface? Which one?
That one.
This part?
Yeah.
Perfect. So we choose the semicircle. We know every point what the B field in the air gap is. And since this is iron, we already said when you have two iron interfaces with infinite permeability in theoretical case, the B fields will always terminate perpendicular to the surface. So the B dot ds term is simply just saying what the B field at every single point would be and multiplying by the incremental surface area and adding all of them up together. That is same as saying setting it as an integral problem. We know what the B field at every single point of this air gap is going to be, right? And we can just integrate the whole thing and figure out what the flux entering is. That will be the same as the flux leaving. And once I have the flux leaving, I can figure out what the differential of the flux is going to be. We already did this when we looked at the case for our permanent magnet synchronous motor. But in any case, let's repeat it. So let's say we have a loop like this. This is a loop for which we are interested in finding the value. And let's say that loop is at some angle beta. So this angle is beta. This angle is pi plus beta. And the B field itself, let's say the BMS space vector is peaking here. And let's call that angle alpha. And we want to figure out what the B field is from this portion to this portion. So let me start off with some arbitrary angle, theta, and figure out what the B field crossing that cross section that I have right there. So the B field there is going to be B of some arbitrary angle theta is going to be equal to some BMS peak, which we can figure out based on the currents that we have, times cos of alpha minus theta. We can quickly verify it. If alpha is equal to theta, if I were to ask the B field along this point, we know that the space vector is pointing along that direction, so that has to be the maximum B field. And that checks out. If theta ends up being alpha, then we have cos of 0, which is the maximum value that it can be. At every other angle, as theta changes, this B field is going to change. Right? So going back here, it's going to reduce. Going back here, it's going to reduce. Going the other way around, it's going to become negative and start to increase and reduce, with the maximum negative being along this direction again. Right? So this is our B field. At this particular angle, we can figure out what the flux is going to be at that angle. Basically take a tiny cross-sectional area. So this is extending all the way back, with the length of this cross-sectional area being L, and this being R times d theta. Right? So it is theta, the incremental angle is d theta. And then the incremental cross-sectional area is just going to be R times L times R times d theta. The incremental flux through the surface is just going to be B times the cross-sectional area dA. So we have BMS magnitude R times L times cos of alpha minus theta d theta. And all we have to do is figure out the total flux starting from angle beta to pi plus beta. So we have found out the flux going through this tiny cross section, going all the way through the axial length of the motor. Now we just have to figure out the whole flux starting from this end to this end. So we have set it up as a nice incremental problem and figure out the total flux, just integrate it, and you go from beta to pi plus beta, RL times BMS peak cos of alpha minus theta E theta. You do all the integral and figure out the value. That would come out to be RL BMS peak 2 times sine of alpha minus beta. Okay, so where will the now we have to get the EMF. So EMF of the loop is just 1 times d phi flux crossing the loop divided by dt. Do the differential 2 times r times BMS space vector BMS magnitude times what do we have cos of alpha minus beta times do I have any other term missing? So we figured out this was the flux in the loop. If I differentiate the flux, the answer comes gave 1 times d phi by dt. I'll get the EMF across the loop. Is the differential complete? Am I missing any other terms? What term am I missing? The variable of differentiation was time, right? So that d alpha by dt, right? We don't do d beta by dt. Beta was just an arbitrary angle that I choose for a loop, right? That's a fixed entity. So the variable that's present there is alpha, but my variable of differentiation is t. So we have d alpha by dt. What is d alpha by dt? What does it come out to?
Mechanical frequency?
Is it the mechanical?
Or no, the electrical frequency?
Why electrical?
Because the the EMF frequency has to match the electrical frequency.
Right? But what is alpha in the diagram? What is alpha pointing to in the diagram there? Basically the location of the stator space vector. Right? And what speed does the space vector rotate at? Can be the electrical speed. Right? Because when you have stator currents and you have some electrical frequency, let's say 60 Hertz, 2 pi times 60, and you plug in those 3 currents into the space vector transformation, you would have ended up with the formula e power some Im 3 by 2 times Im e power j omega t. And that omega would be same as whatever the electrical frequency is, the rate at which the sine wave change. Because if we start from some value and end at the same value, the space vector should have completed a full rotation. Right? So and they would complete the rotation at omega e. So this term is whatever your electrical frequency omega e is. Right? So let me replace with let's call it grid frequency. Of course, PMAC can't be directly connected to a grid without some kind of setup to get it started, but just to make it clear. So 2RL BMS peak, some omega E or omega grid, whatever term, alpha minus beta. Okay. Which of these bars would, in my diagram going back here, so this angle is, I choose alpha. Which of these copper bars is going to have the maximum EMF across it? So what is the equation saying right there? That equation that I have there, E of a loop is equal to 2 RL via BMS peak times cos of alpha minus beta times omega E. This is basically saying that alpha is the point where the stator magnetic field is its maximum. Beta is a random angle that we chose for one single loop. If you want the voltage for some other loop at some other angle beta, this value starts to change. Right? So which of these loops would have the highest EMF across it? Perfect. So the one that's pointed along the BMS, right? If beta becomes same as alpha. So if the conductor loop rotor bar, if it's at the same angle as the maximum magnetic field angle, this is the bar that would have the maximum voltage across it, right? And everywhere else, the voltage will start to fall sinusoidally. So here would be the maximum, here would be slightly lower, here would be slightly lower, there will be even lower, even lower, even lower, and then it will become negative on the other side, right? So this is the equation for the loop. I can look at just the bar alone, right? I have one bar here, 2 combined creates this loop voltage. Every bar would just be E loop divided by 2. And because these bars are symmetric, the B field that we looked at on the left and right are extremely symmetric. So whatever the voltage is here, the exact half of it will be on the other side. So we have RL, PMS, peak, omega E, cos of alpha minus beta. So as you go around the bar, the EMF is starting to vary in a sinusoidal manner. RL, BMS, peak, omega E, cos of alpha minus beta. Let's say this whole term comes out to 100. Right? So let's then plot what these values look like.
V bar refer to the line going in between the two currents, or is it the individual location? I'm a little confused on what E bar means.
E bar is the net voltage that's across the full rotor bar of a single
Oh, okay.
side. Right? So when we had our rotor segments, so we had one bar go all the way from here to here, and then it's shorted on the back as well. So E bar is the total voltage that is drop across this.
And loop is going back then?
Yeah. So this voltage plus whatever the other side bar,
Oh, thank you.
180 degree away. Right? Whatever that voltage is.
Thank you.
So let's start off with the case where alpha is 0. If my currents where IMs are cos omega t, IM cos omega t minus 2 pi by 3, IM cos omega t minus 4 pi by 3, at what time would alpha be 0? What is alpha? Alpha is the angle at which the maximum BMS space vector is pointing to. Right? Alpha is the angle of the BMS space vector. If I say alpha is 0, what does it say about my time t for the currents that I mentioned? So this is where thinking about getting a feel for space vector is quite helpful. If you had to try to visualize all the magnetic field in the air gap, it becomes too much information to process. So what I'm saying is that the three currents are Im cos omega t minus 2 pi by 3, cos omega t minus 4 pi by 3. Right? At what time would the BMS space vector point towards x-axis?
0.
0. Right? At 0 or any sum of 2 pi omega, whatever the value comes out to. All sine replications of it, 2 pi degrees later. Right? So if I say alpha is 0, then I'm just saying that at time t equal to 0, consider what's going on. That's all the term means interchangeably. So in this case, I'm saying the BMS is along this direction. Right? If my currents were cos omega t minus 2 pi by 3, and then minus 4 pi by 3 for the third one. If that was the case, then I know at time t equal to 0, the current space vector is along this direction. Then my BMS space vector will also be along this direction. Right? And then again, same one frequency cycle later, it will come back to the same position. Right? That's what I'm saying with the statement that alpha is equal to 0. Okay. So now if alpha is equal to 0, what will be the voltage of this bar? Right here? What will be the EMF across that bar?
100.
100?
Yeah, sorry. The currents in the bars, are those induced by the stator?
There is no currents yet. We are not talking about currents in the bar at all yet.
Okay.
Right? We're only talking about the EMF induced across the bar.
So
So now you can assume the bar has infinite resistance.
Okay. But how do we like what does the dot and X mean then in this case? Like,
So you can think of it as a conductor coming out and conductor going in.
okay.
It is just a bar. There is nothing there. But so the idea is if the current is when there is a current and the current comes out of the top bar. So whenever we introduce the term current, when the current comes out of the top bar, it's going to go into the bottom bar.
Okay.
Right? That's all that dot and cross mean. Current right now is 0. That's what we are looking at. So we have this BMS space vector around here. Okay, so this was going to be 100 volts because alpha is 0 and the beta angle is basically the angle of the loop that we have chosen, and that angle is 0 as well. So this is going to be 100 volts. Let's say, what is the voltage at the top bar going to be? The one vertically up? Okay, what is the voltage of this bar going to be? I heard whispers of the answer. Somebody confident now?
Is it 0 volts?
0, thank you. Okay, so because again alpha is 0, beta becomes 90 degrees, so that value is going to be 0. For every other angle in between, let's say at 30 degrees, it's going to be root 3 by 2 times 100 volts, which is 86.6 volts. Here we have 50 volts, again 86.6 volts, because cos of negative 30 is the same as cos of plus 30, 50 volts, and then 0 volts. On the other side, it's going to be negative once you plug in all those values. Negative 86.6 volts, negative 100 volts, and then we have negative 86.6 volts, and then we have negative 50 volts on the other side. Now, let's introduce the concept of what's going to happen to the currents. So before we jump to that, so this is the case where alpha is 0. And you can see that the voltages are sinusoidally distributed on the rotor. It's all quite magical. The rotor bars are exactly the same. There is nothing difference between this rotor bar and this rotor bar. It has nothing to do with the rotor at all. It is just that the way our B field is sinusoidally distributed, it induces a voltage on the rotor bars which are sinusoidally distributed. So without putting any additional effort on creating the rotor structure with different set of windings and everything, we have created a sinusoidal distribution. Right? So let's consider another angle. Let's say alpha equal to 30 degree. Or let's make it a little bit more drastic, 60 degree. You have 1 bar, 2 bar. Okay. Which of these rotor bars would have the maximum voltage across it? For alpha equal to 60 degree. Or basically saying omega t has passed to 60 degrees. Right? Some time has passed and the currents have moved or changed around in the phases, and the BMS space vector is maximum. Maximum of BMS is pointing at 60 degree, or the space vector is pointing at 60 degree. Which of the bars would have the maximum voltage across it? It comes.
So the 60 degree one.
60 degree. So this is our BMS space vector. Right? And if alpha is 60, when beta is 60 is when you have the maximum voltage, and the voltage will be 100 volts here, and then negative 100 volts here. And then across it will be the same thing, 86.6 volts, 50 volts, 0 volts, negative 50. Am I drawing this wrong? Negative 100 volts, negative 50 volts, negative 86.6 volts, and then positive 86.6, negative 50, 0, 50, 86.6 volts. Right? So what we are doing is, as the current space vector moves in the stator, due to the stator currents, the EMF of the rotor is also rotating. Right? So we have achieved two things. When we did sinusoidal distribution of the conductors in the stator, our objective was to change the current density distribution in the stator sinusoidally, which is already achieved from this diagram at any particular angle. In addition, what we have also done is, so we did a spatial sinusoidal distribution to get sinusoidal distribution of the current. And then we did a temporal sinusoidal distribution where we shifted the currents in the three phases by an angle of 2 pi by 3. So that whatever distribution we had is now rotating in space. That is also happening here automatically. Right? But we have created a distribution of the EMF that's sinusoidal. And then the sinusoidal distribution itself is now rotating in space as time goes on. We achieved both the objectives that we needed. So in the case of stator, we had to do quite a bit of work to get this done. So in the case of stator, what do? We put a bunch of conductors here, and then we reduce the number of conductors going a little bit farther out. And then we reduced it even further. And then the same thing on the other bottom side. Right? So this allowed us to get a B field that was maximum here, negative maxima here, slightly lower here and here, 0 at this point. So this was achieved by distributing the conductor density sinusoidally. And we have already achieved that in the first process itself. The second process, as time goes on, what we did is in the A phase, we started pumping currents that are moving sinusoidally. In the B phase, current sinusoidally, C phase, current sinusoidally, and each of them shifted by 2 pi by 3 from one another, so that this whole distribution will now rotate. And that is being also achieved here. Right? And so what, beyond my words, is that it somehow happens just because the rotor bars are exactly the same, and then but the physics of it says that it would create a magnetic field that would rotate creating effectively the same as what the stator was trying to do with so much complication. The rotor is just simply doing it without putting any effort into it. Just a bunch of rotor shortened bars. So now, anybody have any questions? So now let's look at what's going to happen to the currents. So far we have a bunch of rotor bars. Except the resistance is infinite. But of course, these are copper bars. The resistance is extremely tiny. So there's really huge amounts of current that flows in the bar. And so we are going to visualize this, whatever the diagram that I have there. So we have these bars. And then a bunch of bars in the back as well. And then shorted on the side. There is some EMF that's induced across this bar. And then there is some current that's going to flow through this bar because all of these bars are shorted together. I can draw this as an equivalent electrical circuit. So each of these bars has some voltage. If the voltage across the bar is very large, I'm going to use a very large circle. And if the voltage is small, I'm going to use a small circle to indicate the voltage. So let's say the voltage across one bar is tiny like this. And then the bar next to it, the voltage is increasing. So going back to the diagram there. So we have the one on the right. The bar, let's say we're starting at the bar with the 50 volts, and then on the left of it, it's reducing. On the right of it, it's increasing. We are going to indicate that with either a bigger circle or a smaller circle to indicate that the voltage is either increasing or reducing. Then so how many bars did I have? One more for 0. If there is no voltage, 0 voltage, I'm just going to short it. Right? 0 voltage. And then on the right side of 0, we have the voltage polarity reverse. We have drawn that big. And we draw that here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bars. One resistance. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right. So let's start off with something being at the peak. Let's say this is the one that is at its peak voltage. And then on the left of it, the voltage is going to be slightly lower. And then even lower. Right, so this was 100, this was 86.6, this was 50, and this is 0 volts. And then after that, here, this was again 86.6. And the one next to it was 50. Notice that the polarity is the same on both sides. And then once it goes to 0, the polarity starts to reverse. We have 50 with positive here, negative here. Here, negative here, 86.6. 100. Hopefully it comes back and terminates at 0. Positive. 50 volts, positive, negative. And then loop all the way back. We have the 0 short there. All right. Resistance of each of these are the same, R bar. R bar, they're exactly the same rotor bars, right? All of them have the same resistance. Let's say the resistance of this, let's say the resistance of each of these bars is 1 ohm. Quite a lot, high value, but just to make a calculation simple, let's say that's 1 ohm. What is going to be the current through this pathway? It's not as simple as you might be thinking, but in reality, it is as simple as what you're exactly thinking. What will be the current? Take a guess, Ben. 100. So counterintuitive, and yet at the same time correct. 100 ampere. It is as if just that this voltage alone is dictating the current. So let's look at what's actually happening. So let's just consider 2 of those bars alone for now. Let's say we're considering one bar with the 100 volts across it with 1 ohm resistance. And then another one, 1 ohm resistance at the bottom where what is the polarity reversed 100 volts. Right, so I'm just considering this bar and the bar on top of it alone for now. If that was the case, it's quite easy to see the current would be 100 because we go around the loop, the net voltage KVL is going to give you 200 and then 2 ohms on this side. Current is just going to be 100 ampere going through this, coming back through this, right? Now let's introduce another set of conductors. Let's say the one with 50 volts here, and then another conductor, 50 volts here, again 1 ohm each. How do I figure out what the currents are going to be now? So we can just apply superposition, right? It's all linear circuits here. So we can just apply superposition. What superposition says is that you can assume just one of the voltage sources are present, rest are all shorted out, figure out what the current is, then do that for all the set of voltage sources. The current through any network would be the sum of all those currents, right? Instead of breaking them into again a bunch of four separate circuits and solving it, you can do one better. I can break them down into a set of 2 voltage sources and the other 2 voltage sources shorted out. 100, 1 ohm, 1 ohm, and then this in essence shorted out. This in essence shorted out. And the other network is going to be 50. The middle 2 voltage source is shorted out with and considering the bottom 2 alone. Right? The current through any of this, if I want to figure out the current through this network, it will be due to the currents of this source plus whatever the currents of this source is coming out to be. Right? These two combined. Again, I could have broken down the way superposition would like you to do. Have this voltage source alone, this also shorted, and then this voltage source alone, this also shorted. That will give me 2 circuits. This voltage source, this shorted, this voltage source, this shorted. That will give me 2 circuits. Net of 4 networks. Sum them up together and we'll get the results. But this is much easier because I already figured out the case where I just had 2 power supplies, what the currents are going to be. So this is the one that's bothering me, right? So what is going to be the current of this network here due to whatever the voltage source on the top here is. So we can figure out what the current is going to be. Let's say that comes out to some X ampere. What will be the current in this network due to this voltage source? All of these are just 1 ohms. Right, this top voltage source, let's say it passed current of 1 ampere through this network, this resistor. What will be the current through this bottom voltage source? Again through the same resistor. Just pure symmetry. Right? This network is exactly same as this network. The only difference being that this voltage and this voltage are reversed. So the current due to this, if it's X ampere, current due to this is going to be basically the same X ampere but in the opposite direction. Right? It's just going to be X ampere due to the voltage source on the bottom. Right? So what is going to be the net current due to these 2 voltage sources on the resistance in the middle? That's just going to be 0 ampere. So as long as we have an voltage distribution that's symmetric, for every positive voltage that we have in the circuit there, if we have an equivalent negative voltage, those voltages current contributed due to the voltage source pairs would cancel out. At the end of the day, leaving only the current due to the primary resistance, primary voltage source that we considered for the particular loop. So the answer Ben gave is perfectly correct. Take whatever the voltage across this is divided by the resistance, that will be the current. There's a little bit of intricate detail going on behind the background, but luckily for us, these are extremely symmetric, so it ends up being there. So it simplifies our life that the current is just the voltage divided by whatever the resistance that we have there. Okay, so we have our E bar is RL times BR times omega E times cos of alpha minus beta. My I bar is just this whole thing divided by resistance of each of the bar, right? And since my voltage is varying sinusoidally in the rotor bars, that also means my current is sinusoidally varying in the rotor bars, right? Because it's just divided by a factor of R bar, nothing else. Now, when I have a sinusoidally distributed current in the rotor, what is going to be the magnetic field due to this rotor currents? What is going to be the distribution profile of those magnetic field due to the rotor currents? What was it when we had sinusoidally distributed currents in the stator? What was the profile of the magnetic field in the air gap of the stator due to the stator currents? It was again sinusoidal distribution, right? The B field was varying sinusoidally because my currents in the stator was distributed sinusoidally. How did we get sinusoidal distribution of current in the stator? What did we do? What was the magic sauce for the stator to get sinusoidal distribution of the current in the stator?
Sinusoidal windings.
Perfect. The number of conductors in each slot was varying sinusoidally. In the rotor, the number of bars, the rotor bars are exactly the same, but just because of the operation, the way the motor operates, we ended up luckily getting a sinusoidal distribution in the current, right? And that in turn is going to create a sinusoidally distributed B field in the air gap. And the interaction of this field with the stator magnetic field is what is going to produce torque, which we'll derive on Friday. But before we end, see how much time we have here? 5 more minutes. Let's quickly jump into transformers, because the next part that we'll be analyzing will require modeling our induction motor as an equivalent transformer. And induction motors are rightfully called rotating transformers, because what we effectively did is we passed some currents in the stator and induced some currents on the rotor. And these induced currents are interacting with the stator to create torque and so on and so forth, right? So it's exactly working as a transformer. So let's look at a simple line frequency transformer. We have some primary coil, let's say N1 turns, N2 turns. How do we find out the inductance of the primary coil? Anybody remember the formula right off the head? How do you go about finding it? The formula for inductance somewhat beautifully remains the same across motors, across this, whatever structure you have, it has the same pattern. You'll have a mu naught term, you'll have an n square term, you'll have some RL or some area term, and you'll have some length term come in the bottom. So Lm, the inductance of the coil is going to be mu naught n square cross-sectional area divided by L. So this is something we derived in the magnetic circuits lecture, right? Where A is the cross-sectional area. And this is not even, I wouldn't even call the derivation, it's quite straightforward. So you pass some current, you're going to get some flux, and the flux is going to be n times I, right? And then this flux is linking n number of coils, that's how you end up with n square. And the cross-section, so that you'll get some B, and then the B multiplies with this cross-section area to get the flux. That's why you get your flux area, right? And then the MMF would be divided by the length that you have, the total mean length of this core, right? So this is going to be our inductance of our transformer. There's a little bit of difference from an induction motor was a line transformer, which you'll get in a second, where this L would start to vary. And then a mu r term, the relative permeability of the iron core that we have. And L is the mean core length. LM. Okay, let's say I apply some voltage, V1. What will be the voltage on the secondary? Very simple question. Please don't be quiet for this one. What will be the voltage on the secondary? There are only two possibilities. Either way, it's okay. Anybody?
2 over N1.
N2 over N1. Why is it N2 over N1?
It's like the ratio of the coils to the voltages.
Yeah, but what is the physical underlying reason that it has to come out that way?
The voltage balance between the two, like N1 V2 equal to N2 V1.
Why should the voltage be balanced? What is the again underlying? We never, in power electronics, we have heard the term voltage balance again and again, but we never introduced the term at all, and we said we don't use any physics concept that's unrelated to it. Where is the voltage balance coming from? Yes.
Conservation of power.
Conservation of power. You would use that to figure out what the currents is, but not the voltage. Right? Yeah, I could have a voltage of 10 volts here, 100 volts here, and or I could have 100 volts here and then 1 volt here, but the currents can balance out in such a way the power is still balanced. Right? I could have any ratio here and still get the power balance working. I don't need to have it to be N2 N1.
The flux is the same.
Flux is the same, perfect. These are wound on the same pole. So if this is having some flux phi, there is the same flux that is linking the other side of the coil as well. And so So phi linking coil 1 is same as the phi linking coil 2, which is the same as the total flux phi through the core. Now we have an expression for our voltage. V on the primary is going to be equal to N1 times d phi 1 by dt, which is d phi by dt. And then V2 is going to be equal to N2 times d phi by dt. Now from this, d phi by dt is equal to V2 divided by N2. From this, d phi by dt is V1 divided by N1. See, these two terms are the same. So V1 by N1 will be equal to V2 by N2. So your V2 ends up being N2 divided by N1 times V1. Right? So basically the voltage balance, whatever Hannah gave, the underlying fundamental reason is the answer Jonah gave, which is basically the flux is exactly the same in both coils. Right? Okay. If there is no load on the secondary, is there going to be a current on the primary of this transformer? And he's already looking at the time. Just 2 more minutes. If there is no load on the secondary, is there going to be current in the primary coil?
Only losses,
What was it?
only for losses.
Let's assume there is no losses. No, there is, because we have an equivalent inductance there. Even if there is nothing on the secondary, if you apply the voltage, that is basically an inductor coil. Right? Completely forget about the secondary coil. If I had given you this as an exam question, which I actually did, and I give you a sinusoidal voltage, you would have found out that there would have been a current through the coil because it's pure inductor. And what will be the current? Im is the magnetizing current, which is going to be your voltage divided by whatever the inductance of that coil is. Whatever the secondary does is a later part. But even if there is nothing on the secondary side, there is going to be a current on the primary side. And the way we are going to be representing this in an equivalent ideal model is we have a transformer that is just doing some transformation ratio N1, N2, and we are going to put this inductance in parallel, Ln. Right? So now this is an ideal transformer where the same as saying the inductance of the transformer is infinite. When will the inductance of the transformer be infinite? If my mu r, the ideal ion that I have, if it's infinite, then the inductance is infinite, then there is no equal requirement for magnetizing current to establish the flux in the core. But for a real transformer, mu r is not going to be infinite. There is going to be some magnetizing inductance, and that magnetizing inductance is going to carry some current, Im, which is going to be given divided by V1 divided by 2 pi times F divided by Lm. So this should give you a hint of why I did the P by F control in the last on Wednesday demonstration, where I was trying to change the frequency, and I said I proportionally increase the voltage as well. I'll explain it when I get to induction motor. What I was trying to do is basically keep the flux in the motor the same. If the V by F ratio is exactly the same, then the current through this magnetizing inductance remains the same. If the current through the magnetizing inductance remains the same, the flux in the core remains the same. We are trying to maintain the rated flux in the core even at starting point till the end of the speed control of the motor. Alright, so this is what we are trying to model there. Let me take 1 more minute. What will happen to the inductance? Let's say I put an air gap here. In a transformer, if I put an air gap there, what will happen to the inductance Lm? Will it go up or go down? If I were to introduce an air gap, so I said if I had an ideal ion, the current would be infinite. Sorry, current would be, the inductance would be infinite, the current would be 0. Right? If I had an ideal ion, the inductance is infinite. As the core starts to saturate, the ideality of the core starts to come down, and the inductance is starting to reduce. If I introduce an air gap, that is same as saying the core is no longer ideal, it's well saturated. Right? So that would mean the inductance would have to drop quite significantly. So when I introduce an air gap, Lm starts to plummet. So the Lm value with an air gap changes to mu naught n square cross-sectional area divided by L, where L is the air gap length Lg. Previously, the L was the mean core length. That no longer matters because air gap is the one with the largest reactance or reluctance. So that is what is going to be the deciding factor. It's like connecting a huge resistance with copper wire. Copper wire is not going to offer much of a resistance, right? So this is going to be a new inductance. So in case of an induction motor, this inductance would be quite small compared to a line transformer. In case of a line transformer, there was no air gap, so the inductance Lm in this case would have been extremely large, and in this case, Lm would be quite small. So for an applied voltage, the magnetizing current in a line transformer would be very small. In case of an induction motor, that line current would, the magnetizing current would be extremely large because the inductance is very small. So if this Lm is small, if Lm goes down, your Im goes up. Right? So in case of a magnetizing, in case of a line transformer, your magnetizing current would typically be 1% of your rated current at the worst case. In case of an induction motor, the magnetizing current component would be as high as 30% of your rated current. Alright, so to set up the magnetic field in the air gap, it requires so much amount of current. That's what makes it extremely inefficient. In case of a transformer, absence of this air gap makes it quite efficient, where the magnetizing current is just a tiny portion. Can we do away with this air gap? Not at all, right? Because we need some separation between the rotor and the stator. It's a rotating element. The mechanical isolation is provided by the air gap. But what we want to try and do is reduce this air gap to as small a value as possible. So typically large power induction motor, this value can be as low as 0.1 millimeter. Right? Extremely tiny. In case of a permanent magnet synchronous motor, you could not make this air gap very tiny. In case of an induction motor, you can make this air gap quite small. And you will want to tell me what the reason would be? Typically, yep, John.
Is it because in the magnet, in the permanent magnet motor, you had to like carve part of the magnet out to make the sinusoidal field?
Perfect. So we have two reasons. One, perfectly the answer Jonah gave, where we have to carve this magnet, shape this magnet in such a way that the air gap length is varying. That is what was creating the sinusoidal field. There is a second one where these magnets are basically stuck on to the rotor with some glue. As the rotor starts to rotate, the magnets are going to experience a centrifugal force that are going to pull them out. If the air gap length is so tiny, then these magnets will start scratching against the stator as the magnet starts to rotate too fast, as the rotor starts to rotate too fast. And magnets being brittle will crack instantaneously. One way they get around this is the people who have done these hub motors when you use quadcopters. They put the rotor structure on the outside so that the centrifugal force will push away from the air gap the magnets. Magnets are stacked on the outside or the rotor is on the outside. So the air gap length would actually increase as you go to higher speed so that it won't strike against the stator structure. Right? But in case of an induction motor, we don't have any magnets. We have solid rotor bars. You can tighten them so quite effectively that as it rotates, there is going to be no stretching on the rotor bar. So you can get this length to be quite small for an induction motor, but for a permanent magnet motor, this will typically be around 0.5 to 2 millimeter. Right? But in an induction motor, you can get this so tiny that the inductance is relatively small, and even in that case, you would have like 20 to 30% of the current being the magnetizing current. With this, we'll continue on next week.